Okay, good afternoon to all. So today we are going to start a new topic, and can you all hear me?
Yes, sir.
Okay, my screen is visible to you.
Yes, sir.
Okay, so let us start with something interesting topic. So, finite difference operator. Finite difference operator. So, we all know that a Taylor series can be expanded in the form written that in terms of x xi plus one. So I xi plus 1 is the this coordinate on the x-axis, and xi is the previous coordinate. So we can expand this function using Taylor series expansion. H is the step size, which is calculated as xi plus 1 minus xi. So xi is the point on the x-axis, xi plus 1 is the point on the x-axis, and xi is the previous point. So this difference gives the step size. So numerical differentiation. We all know that the conventional formula to obtain the numerical differentiation, but how to find it using some numerical techniques. We will see this in see here. So suppose that you have a Taylor series expansion, and you take neglect that power of this from this h square onwards. You neglect the power, and this f prime is nothing but slope. If you carefully look, this is a slope, and rest of the term, that is of order h square, we neglect it, or say as error. That is error. If we are going to neglect the higher order terms, then obviously the solution will not be exact, and there will be error involved, and this we call it as an error. So if you rearrange the term of the Taylor series equation by neglecting the h cube term, and other higher order terms, that is h raised to the power 4, 5, and so on, you neglect those terms and take only terms up to h square. That is we call it as error. So once you rearrange this, then the derivative, first derivative, can be expressed in terms of this value of function at point xi plus 1, value of function at xi, and divided by the step size. So you can see here this, we have three techniques to do this, to calculate the this derivative, first derivative, using numerical technique, because computer doesn't understand your this this conventional technique of obtaining the differentiation. So we need to program this, and for that we are studying these methods. So one is forward difference method, second is this backward difference method, and third is central difference method. So please have a careful look on these three figures. One is figure A, figure B, and figure C. So figure A, you can see here that on the x-axis we have one point xi, and one point is at xi plus 1, that is at an interval of h. So the shorter this interval is, the more accurate results we get. But you see this, if interval is large, then we have a true derivative, that is a tangent at point xi. We can calculate it using dy by dx, and however, with the approximation that is we are dealing with in this topic, that is forward difference method, backward difference method, and central finite difference method. you can see that the slope of true derivative is different from the approximation. And if this approximation, if we take the step size in a forward direction, we call it as a this forward differentiation, this forward difference method. And if we take a step size at this in backward direction, as shown in figure number B. So here you can see that this is again is an approximation, but we called it as backward difference method. And here also you can see that the slope of approximate line is not again means is same as that of slope of derivative. So the two slopes are different. So uh, however, you can see in central finite difference method, the slopes are nearly equal, but the step size has increased from h to 2h. That is, we are dealing between interval xi plus 1 and xi plus xi minus 1. So this forward difference is but one of the many that can be developed from Taylor series approximation. So we derived this forward difference method, and other technique can be backward difference, central difference approximation of derivative can be developed. So let us talk about this backward difference method. So what is this backward difference method? So we have obtained this Taylor series expression. So and using this Taylor series expression, what we can do is is towards we square it, then it will automatically give us a positive value. So here you can look, this is backward difference method. That is, we have obtained this function using same Taylor series expansion. So, but you can see that there are some negative terms, and negative terms are only for in which h is raised to power odd powers. That is h raised to power 1, h raised to power 3. So, uh, okay, can you hear me?
Yes, sir.
Okay,
Yes, sir.
yeah, screen is means moving to in.
Yes, sir.
Okay,
Yes, sir.
okay. So in equation B, you can see equation number B. Uh, if we assume if we take h raised h square term as error, that is, we are considering only terms up to h, and beyond that we assume that it is an error. So in order to find the derivative using backward difference method, we can rearrange this equation above b equation above b, and express derivative in terms of this backward using backward difference method. So these are the two techniques. One is forward difference method, one is backward difference method. You see that whole term is divided by h, and also the double derivative term, once it is divided by h, So only a single power of h is remained. That means what uh, if we have an error of zero point 0.5 in this method, so same milli introduced, and we have a error of order unity. So this will be more transparent to you on solved example. One more method we have, it is a central difference method. So in the figure you can see that true derivative, the slope of true derivative and the approximate derivative in figure number C are nearly equal. The two slopes are nearly equal. So the derivative value of derivative obtained using central difference method will be more accurate in comparison to previous two approaches. So here you can see that we have equation number one, equation number two. I have just simply written this forward difference method, and one is backward difference method. So if you subtract this one from two, and on rearranging these terms, you can easily solve this, rearrange these terms. You get something written here that this f xi plus 1, and it is expressed in terms of both step size in forward direction as well as step size in the backward direction. So once you rearrange this, in order to get the first derivative of this, we will divide it by this step size, and you see that in this central difference method, that is equation number 3, we have an error of order h square. That is we will see that how error is much more reduced in calculation, while performing calculation using this central difference approximation. So uh, equation 3 is a central difference representation of first derivative. Notice the truncation error is of order h square. It is the truncation error is of order h square, in contrast to forward and backward approximation that was of order h. Consequently, Taylor series analysis yields practical information that central difference is more accurate representation of derivative. For example, if we halve the step size, suppose that step size, that is xi minus xi plus 1 minus xi, and its value is equal to zero point 0.5, and if we half this step size from 0.5 to 0.25 using a forward or backward difference, we would approximately have the truncation, half the truncation error. So once we this make the step size half for the and to perform the calculations for the derivative, first derivative of any function using this forward or the backward difference method, we have a truncation error just half. Once we do this step size, reduce this step size to half. However, if we reduce the step size to half and perform and calculate using the two different step size, one with the initial step size h and one with step size of h by 2. So in central difference method, the error will be quartered. So suppose that you have an error of previous error of zero point 0.5, and on reducing step size uh, to half, now the error will be square. So zero point 0.5 square, this will be much more, this will be, error will be approximately 0.25. Now once you do this for using central difference scheme, then this error will be 0.5 raised to power 4. So this error is much more truncated, or the solution is exact using this central difference uh, scheme. Now let us proceed towards one solved example. So who can tell the exact value of this function, derivative of this function? at x is equal to zero point 0.5. What is the exact solution? It is already written. You say do it on your own. So the exact solution is minus 0.9125. However, uh, we are interested in performing, or we are interested in calculating the derivative of this function, that is minus zero point 0.1 x raised to the power 4 minus 0.15 x raised to the power 3 minus 0.5 x raised to the power 2, and so on. So we are interested in finding the derivative of this function at x is equal to zero point 0.5, and using two different step size, and the three techniques, numerical techniques, that is forward difference method, backward difference method, and central difference method. So corresponding to h is equal to zero point 0.5, we will have three answers for each of these approximations. However, for h is equal to 0.25, we will have three set of different answers. So which will be more accurate? Can anybody answer? H is equal to zero point 0.5 and H is equal to 0.25. These are the step size. What is this step size? We have already discussed. So now let us calculate this using H is equal to 0.5. So H is equal to zero point 0.5, that means xi, if you assume 3 points on x-axis, one is xi minus 1, one is xi, and one is xi plus 1. So step size of this the interval difference will be of 0.5 between each of these steps. So our next immediate task will be to calculate the value of these function at xi minus 1, xi, and xi plus 1. So once you do this exercise, and substitute the values as discussed now for the uh, forward difference method, backward difference method, as well as for central difference method, which is written in right hand side. You substitute the value of function, you get the value of function, derivative of function at x is equal to zero point 0.5 as minus 1.45, and which is absolutely incorrect, and the percentage error with respect to true value is 58.9%. However, once you use a backward difference scheme and compute the value of the derivative using the formula written in your this right hand side, that is f prime xi is equal to f fxi minus 1 upon h is the h value of h is 0.5. If you perform these calculation, you get the and error of 39.7%. Now let us solve this example using central difference scheme. So our central difference scheme formula is written in our right hand side. You can see we have the value of function at xi plus 1 and value of function at xi minus 1. If you substitute it in this formula, you will get the value of function, and using three schemes: forward difference, backward this is for a step size of 0.25. So you will get this answer as using central difference scheme, you get the answer as approximately an error of 2.4%. Okay, so uh, once we have solved this using step size of 0.5, you can see that employing central difference scheme using a step size of 0.5 gives an error of 9.6%. Once we reduce this step size to 0.225 and use three schemes, that is forward difference, backward difference, and central difference, so we can observe that the central difference scheme gives much more accurate results, with an percentage error of only 2.4. So for both step sizes, central difference approximation is more accurate than forward or backward difference. Also, as predicted by Taylor series analysis, halving the step size approximately halves the error of backward and forward difference and quarters the error of central difference. So you see here that uh, uh, value of this derivative computed using central difference scheme, the error was 9.6%. When once we reduce the step size to 0.25, error was just 2.4% using central difference scheme. Similarly, if you see this forward difference scheme, with step size of 0.25, we have 26.5% of error. And here you see that the error using step size of zero point 0.5, we have 58.9% error. So error is almost half in using this forward difference or backward difference. However, we have to reduce the error by fourth. So you solve one example on your own and give the answer for this. So who can answer this? What is the exact value of this derivative of this function at x is equal to 2? Anyone? So I should ask from you people. Abhijit,
Yes, sir. Sir, I'm getting the black screen, sir, due to network issue.
so you're not telling anything.
Sir, I
Ayush,
said the
please wait. Ayush, let me check.
33.
यस सर ट्राई कर रहे सर
स्क्रीन विजिबल है मेरा?
Yes, sir.
Can you give the exact value of this function at x is equal to 2? Derivative of this function at x is equal
283.
to 283. Okay. So can you employ the three different schemes just now we discussed in order to calculate the value of derivative? So what formula we will use? I will once again go back and show you. First you note down this function 25. What is this function? 25 x cube minus 6x square plus 7x minus 88. So this is the function. So what will be xi plus 1? Who can answer? Null. And what will be xi minus 1?
1.8.
1.8. So what will be the value of value of function at xi plus 1?
343.6.
Okay. And f of xi? F of xi, that is value of function at x is equal to 2.
102
102.
And value of function at your 1.8.
50.96.
Okay. So we will employ this scheme, that is forward difference scheme. What does this forward scheme says? So this is approximately equal to f value of function at xi plus 1 minus value of function at xi divided by h. What you are getting? Value of function using forward difference scheme.
312.8.
3 1. Oh, answer, and this answer calculated using this forward difference approximation. Okay, so this is all you are getting for forward scheme. C for and that E. Ankit also the exact answer for this. So we have this. You can always calculate value of function using this for forward difference scheme. Backward difference scheme, you can see here that this is f of xi and value of function at f of xi minus 1 divided by step size h. So anybody got the answer for backward using backward difference scheme? Okay, exact. Ayush has written 283. Okay, backward answer is 5. And central difference. So central difference scheme, I will once more show you the formula. Here you can see value of function at point xi plus 1 minus value of function at xi minus 1 upon 2h. So anybody calculated the value of function at using central difference scheme? The exact answer is 283. Central difference 284. Okay, Dhruv has given this answer as 284. So we are studying these techniques because in computer you have to use this you have to program these methods because computer doesn't understand this dy by dx whatever we have use in our conventional scheme. So we use these numerical techniques in order to calculate the derivative. In similar way, we'll see some of the methods how to calculate the integration in our further classes, subsequent classes. Calculate else. Abhijit,
Yes, sir, doing it, sir.
so why you are taking so much time? Who else?
Sir, but derivative calculators are also available online. So
Will on this exercise, then we will discuss this after the class. Okay, Somil has one given. Raja Kumar, Rajdeep, Priyanshu Singh. Okay, so only few people are always giving answers. Okay, so one more example we will also see in our next class, because due to this shortage of time, we will restrict our this class. And one more solved example. Already you have, people have given the correct answer. So one more example. This is solve question number 2. Compute the forward backward difference approximation of OH, that is this first order approximation, and central difference approximation for the derivative. First derivative of this, you calculate the first derivative at x is equal to pi by 4. So who can tell me the exact answer for this? What is the exact value of the derivative of function y is equal to sin x at x is equal to pi by 4?
1 by root 2.
1 by root 2.
Okay.
Why 1 by root 2?
So
1 by root.
okay, very good. So why don't you give the this 3 answers for the forward, backward, as well as for using central difference scheme, which you solved just now for this function. You give the answer for this trigonometric function. Once you question number as your assignment. Banti Kumar Das, Kumar Patel, Lishti Saha, Dhananjay Kumar, Gaurav Kumar, Jyoti Kumari, Kriti, Krishnam Kumar, Kumar Raj Kritya, okay. So Linal has given answer as 0.263. So what is the exact answer in terms of expressed in terms of decimal values? You may also write it in the chat box. Okay. So Ayush, what is this answer using forward difference approximation? Okay, Dhruv has given point 0164. Anyone else? Okay, Ankit, forward point 6. Yeah, this seems to be correct. Point 607. Ankit, you perform this exercise using central difference approximation. Next class, we will see how to. Today's class, we have first order. This we will see the second derivative. We will compute the second derivative using these three numerical techniques: forward difference method, backward difference method, and central difference approximation. Okay, Ayush has given this answer. Central 0.84. So Ayush, what is the exact answer? Is it 0.71 as the
Yes, sir. 0.707.
0 point? You write it in the chat box, no? Okay. Once you have solved this, you can go for this question number 3. And even if you have solved this question number 3, you may
Interest.
take this